Okay, we are live. All right, hello everyone. So today we are beginning the sections on differential equations. That's ordinary differential equations. Okay, so we are going to be looking at the exercises. So let's join up. Okay. The description seems not to be correct. This should be part 1. Let me see if I'm able to edit. Okay, I will edit this. Okay, I will edit this at the end of the session, because this is just the beginning part of this particular one, and so it should be part 1 of module 1. Okay, so let me even write it here. So we're beginning with part 1. Okay, so part 1 implies that we are in module 1 and we do not know the number of questions. Let me give a breakdown of what we have. Okay, so for instance, now we have about 8 Okay, yeah, we have about 8 problems, that's 8 questions when it comes to module 1. Okay, so that's what we're going to be covering here. Okay, so let's go back. So we have about 8 problems, so we do not know, that's 8 questions. We do not know how long it will take us. That will determine the number of parts that we're going to have in this particular module. Okay, so let's begin. All right, so good evening everyone. So like I said, this is ordinary differential equation, ODE, Math 202. Okay, yes, again, this is a course in the university where I teach, and it has these exercises. Now, however, it's a general mathematics that is not particular to where I teach, so anyone can learn from it. So what we are doing is to solve problems in the exercises that they are given, and then it will form a part of a quick general review of the whole course. All right, so and then later on we will now come up with a full development of teachings on the course itself. Okay, so we will take the topics of the course one after another, so which is going to include introduction, what is differential equations. Okay, so after which you look at stuff like formation of differential equation, solution of a differential equation, what is the solution of a differential equation, what's the definition. Of course it's going to be a function. Okay, so and the question is, because how is it a function? Because you know that differential equation, from introduction we are going to see that a differential equation is gotten by differentiating a function. So for instance, if I differentiate y equal to x squared with respect to x, I'm going to get 2x. Okay, so by the time you take over this 2x this way, remember we said that you can write the y dx as y prime. So if you take this over here, you will have minus 2x equal to 0. And a differential equation is generally defined as an equation that contains some derivatives of the dependent variable y. Okay, so once there is the presence of a derivative, then you refer to what you have as a differential equation. And so for you to actually get a derivative, then there must be a differentiation that occurred. So now, if I now have a differential equation and you want me to solve it, the implication is that you want to get back the function that produced that differential equation. Okay, so in other words, you're saying you need the function that will satisfy this, meaning what value of y will I take the derivative and subtract 2x, and then I will get 0. Okay, so that's exactly what solving a differential equation entails. And what that means is that you are actually looking for a function. The solution is a function. Okay, so right, let's see. Okay, let's go back to where we were. Oh, okay, sorry, I was trying to mention some of that. So I was saying that what was the definition for the solution of a differential equation. I've already defined that, and then we are going to take examples of on that, which will which will include asking the question of which is this function a solution of a differential equation or not, okay, you know, and all of that. Okay, so and all of those basics of ordinary differential equations. So that's what you touch in the first part, okay, and then in the second part you will now begin the proper solution of differential equations, and there you are going to meet about 5 different kinds of differential equations and how to solve them. Okay, so we will, in that case, you're going to see separable equations, or maybe 5 or more than that. So you're going to see separable equations. You're going to see I'll just mention them, of course, not in any order. So you're going to see homogeneous equations and how to solve them. Homogeneous equations. After homogeneous equations, you are going to see what we call what are the names now? Bernoulli's equation. I didn't want to call this one now. Okay, but let's go. So you are going to see Bernoulli's equations. You are going to see what we call exact equations. Okay, and others. There are actually others. I think another one that will make it about 5 different kinds of equations that we are going to treat, to look at how do you solve them. And the reason we are teaching this is because if we want to now ask you to solve a particular differential equation, most times we don't state the type of the equation. So you are the one who is able to decipher what type of equation, because that will inform what approach you are going to take. Okay, so and then there are other parts of this that we are going to see, but these are the basic 2 parts in this particular course. All right, so and in these exercises you are going to be seeing questions involving all of these that I have mentioned. Okay, so let's quickly start, and then like I said, by the time we are done, then we will come back and begin to learn the topics generally. Okay, so let's begin. Problem 1. Okay, so the first problem is a copy and complete. This is basically review of the prerequisite course for this particular one. Of course, you know that nothing stands on nothing, okay? So every course that we do, even in our first year in the university, stands on something, all right? So those ones stand on the things you have done pre-university level, okay? So now the same applies to this course. It has a prerequisite, and the prerequisite for this course is Math 102. So, and I've also covered the exercises on 102 on this channel, and the content as well is going to be taken care of. Okay, so 102 is pre-calculus, so you can just say calculus, all right? So where you have functions, differentiation, that's differential calculus, integral calculus, and then we have conic sections there. So but this particular course will measure on derivatives and integrals of functions. So that those 2 major areas of Math 102 are the prerequisites for this course. Okay, so majorly integration, and so we are going to be taking this question is coming from that particular area. Okay, so let me write out what you've got, and then we'll begin to respond to it. Okay, permit me to reduce this because we are going to be needing it. Okay, so I think this is much better. Yeah, I think this is much better. Okay, so let me also get a line here. I think it will help. Okay, I think that thing doesn't look straight. Okay, so even this way, let's get something this way. Okay, because it's a table that you expected to complete. Okay, so assume that this is Sn, the serial number. Then here you have functions. And then here we have antiderivative. Okay, so here the function is called f. Here the antiderivative is called g. Okay, so of course you know the meaning of antiderivative. Alright, that's another name for integral. So in other words, what they are asking us here is, if you are given a function here and here is empty, it means they are asking you to get the antiderivative of whatever function that is given here. And I think that's what they started with. This is 2x, so they want you to get the antiderivative of 2x. Number 2, here is x squared, antiderivative of x squared. Number 3, okay, this one now is vacant, and so here we have minus cos x. So in other words, we should get the derivative or the function whose antiderivative will be minus cos x. Okay, then number 4, we are given sec squared x, so we are to get the antiderivative. Number 5, okay, number 5, the derivative, the antiderivative is given x raised to power n plus 1 all over okay, so that and then the last one, we are given number 6. Here we are also given the antiderivative. Okay, sorry, somehow like this, d dx of the integral from x, or let me use this there, integral from 0 to x of e to t squared, e of t squared. Okay, so I believe that this should be with respect to t, even though it's not given. I think it's an omission. Alright, so this is the beginning part of the exercises, and I'm going to allow you to think through. Let's see what you think. Okay, so over these ones, let me see if I can go down a little bit more. I hope it's still visible. Okay, so think over it. I'll be back in a moment. All right. Okay, so welcome back. Now, so what is it that we should do here? So what is it that we should do here? Okay, so now let's look at it now. So the first is that we are looking for the integral of this. Remember I said antiderivative is the same thing as integral, and so that is why I said it's just a recall of what we did in Maths 102. Let me try to increase this. I think I reduced it because I wanted everybody to see the board. Okay, so let me remove that, and then okay. All right, so this is okay now. Okay, so let's quickly look at it. So now we are looking for the integral of 2x. Of course it will be with respect to x, right? So that's going to be, so we are actually looking for okay, so what's the formula? First of all, if I have the integral of x raised to power n with respect to x, it is given as x raised to power n plus 1 all over that new power, which is n plus 1, and then when you are done, you can add your constant c, or in most cases we ignore that constant, especially if you watch what is happening here. This antiderivative should have a constant c, but it was ignored. So if it is ignored, whether you yourself should always bring that in. All right, so this is for the integral of polynomials, and then of course you can see that's what this represents. Okay, so if we are to integrate this, now of course the constants will just come down like this, and then it's only the x that we are going to integrate. So remember that the power here is 1, so that's going to be 1 plus 1, which is 2, then all over 2, and then plus constant c. So if we now simplify that, then we are going to get the required solution that they want here, which is, of course, this will cancel this, and so our answer here is going to be x squared plus c, and you are done. That's actually what they want in that position. All right, and then for the second one, which is x squared, you want to integrate x squared with respect to x, of course. So that is going to be x to the power of 3 all over 3, and then you have plus c. Okay, so that's all. Like I said, this is just a form of review of all that you did in the prerequisite course. Okay, and more especially, not all, not all anyway, so I don't mind my this thing. Okay, so that is just to make you have a review of the important part for this course in that prerequisite course. Okay, all right, so let's go on. Now for number 3, you are given the antiderivative, that's the integral, and you're asked to get the derivative. That means the function that produced that derivative. All right, so let's go ahead. So to do that, of course, when we talked about standard derivatives in Maths 102, the prerequisite course, one of the things we saw is that for trigonometric ratios, that the derivative of sine is cos x, and the derivative of cos x is minus sine x. Okay, and the derivative of tan x, tan x was sec squared x. Okay, so if you now want to take the antiderivative of okay, now this one now is derivative, so that means if I take the antiderivative of cos, I will get sine. If I take the antiderivative of minus sine, I will get cos. That means if I take the antiderivative of only sine, then this minus will come here. It will become minus sine and minus cos. So actually, the antiderivative of minus cos should actually give sine. How? Watch it here. So if you take the antiderivative of that, so what will it look like? So look at it here. So this in integral, remember you are integrating with respect to x, so I'm just putting that on silent now. So the integral allows that you can bring out a constant. So I perceive not perceive now. We know that this is the same thing as the minus. You can put minus 1 if you want, but I prefer to leave it as minus. So this is the same thing as the minus integral of cos x with respect to x. Okay, so and then you are done. So what is the integral of cos x? Oh, I just removed what I needed. Okay, so what's the integral of cos x? That's the antiderivative. If you have cos x and you want to get the function that gave it, what will it be? So that is this one. Okay, so and that means this is equal to the integral of cos we said is sine. So this is giving us minus sine x. Okay, so okay, permit me to get what I'm looking for now. Okay, now look at what we are saying. Okay, so now I have minus cos x. So what is the function that was differentiated? Okay, this is antiderivative. In other words, this is integral. Okay, so we are looking for the function whose integral is this. In other words, so in other words, yeah, what we needed to do is to differentiate this one. Okay, you know, if you differentiate this, you get the function that gave this integral. Sorry about this. Okay, so what we're supposed to do is to differentiate, just like in all these cases. You know, if you differentiate this, you get this. If you differentiate this, you get this, and so on. So what they're asking us here is to differentiate minus cos x. That means what function was differentiated to get this. For you to get that, just differentiate this one. That will give you what was differentiated. All right, so let's quickly do that. And like I said, under that integral, so the minus sign can also come out. So you have minus sine, minus of the derivative of cos x. And so, and remember we said the derivative of cos x is minus sine x. Okay, so and if you do minus minus, that's going to give us sine x. Okay, so you know I said earlier that it should be sine x. So it was after I did that integral and it was not giving me sine x. I now knew that there was a mistake somewhere. Okay, so it was not integral I was supposed to do, but it is derivative. Okay, so in differentiating this, we will get the function that gave the integral. All right. Okay, so and that is that. And then the same thing happens here. So here you are looking for the integral of this one. So what's the integral of this? That's of course the function that when you differentiate it you will get this, and the function that when you differentiate you get this is your tan. So of course you can put plus c there. Okay, and then we go over to number 5. So for number 5 of problem 1, you are asked to get the function that when you differentiate it you will get this one, and in other words, the function that when you integrate it you will get this one, and that's actually x raised to the power of n. In other words, they're asking us to differentiate this one. And if you differentiate this, what are you going to get? Let's quickly try it. So let's assume that our y is equal to x raised to the power of n plus 1 all over n plus 1. And we want to differentiate this. So that means our dy dx is going to be equal to, remember the approach for differentiation says that you should remove 1 from the power. So if we do x raised to the power n plus 1 minus 1 all over that new power, which is, the power will multiply, So the power will come down to multiply, that's n plus 1 will multiply x raised to the power of n plus 1, and then you subtract 1 from the power, and then remember that there is an existing fraction there, which is n plus 1. Okay, so you discover that what will happen now is that n plus 1 will cancel n plus 1, and then 1 here will cancel 1 here. So you only have x raised to the power of n. And that's actually what you have here. This is, if you take the integral of this is what you get. And I know I defined that earlier on. Okay, so that's the beautiful part of math. So you can go from any point to the other. All right, so and that's for 5. Okay, so now let's go to 6. Okay, so for 6, excuse me. Okay, so for 6 now, the question is asking us to, all right, get what, okay, you know, like the derivative that will produce this, okay. In other words, it's asking us that if we differentiate what we have here, what are we going to get? So remember all other ones that we did. Like here, the derivative of this is this, the derivative of this is this, the derivative of minus cos is actually sine, the derivative of this is this, and so on. Okay, so here we are asked to get the derivative of this function. Okay. Okay. All right, so let's look at, first of all, what is the function? So let's try to evaluate this function, because I believe that this was coded so that you will be able to solve it first to get the function, and then you can now get the derivative. Okay, so what's the function here? Now you can see that this function is the derivative of an integral, so we need to integrate first. So to integrate this with respect to t, you're going to have the same et squared, and then now you would divide by t, the derivative of the power here, and the derivative of t squared with respect to t will give you 2t. Okay, so and then you will evaluate this because it's a definite integral, so you evaluate it from 0 to x. Okay, and if you do that, you are going to have d of dx, or d dx, sorry, of, now remember in substituting, you will put your t as x, which is a upper bound, so we'll have e of x squared all over 2x, then minus, remember you subtract the substitution of the lower bound, and in substituting the lower bound, you are going to put your t as 0, and that's going to be e0, and you know e0 is 1 all over, then you put your t as 0, so you will discover that that will give you 1 all over infinity, 1 all over 0, which will be undefined actually. So which will be undefined. Yeah, it will be undefined. Okay, so here is going to be 0, so you have this minus infinity. Okay, so now meanwhile, if you watch, you discover that this is not giving us something that will be reasonable. So let's look at it in another way. So which other way do you think we can go through this? Let me use a simpler example to see what this will look like. Let's assume we have ddx of the integral of 2x. Okay, so now you know that the integral of 2x, of course that one is straightforward. The integral of 2x is x squared, like we did up. All right, so and by the time you differentiate this, you will get back your 2x. Okay, so in other words, you see that integral takes away derivative. Okay, so but the only issue in this case now is that it's a definite integral. All right, so and it's going from 0 to x, so we needed to evaluate those the values from 0 to x. So assuming that this was an indefinite integral, then this would have taken away this. Okay, but here you have a definite integral just going from 0 to x. Okay, and then so that means we will come back to what we did because it's in order. All right, so you discover that this is going to be this integral is correct. Yes, the integration of a function of function like e now is to bring down your this the way it is and then divide by the derivative of the numerator, because when it is in a differentiation, you bring it down that way and multiply by the derivative of the power here. But in this case, since it is the reverse, when you bring it down that way, then you will divide by the derivative, and the derivative of t squared is 2t. Okay, so if we substitute x, we'll get this all over this minus, if we substitute 0 up here, we'll get 0 squared, which is e0, and e0 is 1, all over 2 times 0, which is 0, and that's not defined. So this one is not defined, which is, you can call that infinity. And anything minus infinity is actually infinity as well. Okay, so that's sorry, no. This is not, sorry, my I was supposed to have started this on a new page. Okay, all right, sorry about that. We had a beautiful section with my students, and that's that board you just saw. Okay, so now you can see that this is also infinity, and the derivative of infinity is also undefined. So that means I will write undefined here. Okay, so I would take it to be undefined. Okay, so but apart from that, if it was from 0 to, sorry, if it was what do you call it, well, assuming that the integral we had here was, an indefinite integral, then we would have gotten a value here. Okay, so Okay, so let's leave it that way. Okay, so it's undefined. All right, so now that's for problem 1, but look at it again and see if that is okay, and then whatever you think, let me know. Okay, so let's go to a new page now. Okay, and of course that's the end for problem 1. Okay, so the next one is that we are given the next question, which is problem 2. Okay, so there we are asked to evaluate the derivative of the integral, just like the last thing we did now, but it is going from 1 to s cubed of the sine of t with respect to t. So just like what we did. So however, the material we have gave some hints, just gave some of the steps and expected us to fill up what we have. Okay, so but we are going to be doing the solving here in full, and then you can then fill up other necessary things. Okay, so it says, first of all, the hint says we should let u be equal to sine t, x cubed. Okay, so we are giving this a name. Okay, we are calling it u, and if we call it u, so it implies that okay, so we chose to now, or the hint says we should get du dx, so which is 3x squared. If you differentiate this, you will have that. Okay, so now this name calling here now changed some things in the function we are given, so particularly this bracket. So our integral of s cubed, integral from 1 to s cubed of sine t with respect to t now became a function of x. So of course at this point you have the function you are given to integrate is a function of t, but by the time you finish integrating it and you substitute this, it will be a function of x. However, what is this going to become? But when you now finish integrating and makes it a function of x, then you will still have to substitute your x with u, and so you are going to get, so the question there now says that what is this now going to be a function of? So if I finish the integration and then substitute what is necessary, so they are asking what function will this now become? So of course it will be a function of u. Why is it so? Let's look at it. If we integrate this, we are going to have integral from 1 of x, okay, so if we integrate sine t with respect to t, we are going to get minus cos t. All right, and since it's a definite integral, it will go from 1 to x3, and then that is going to give us, so the substitution will be minus cos x3, then minus, you subtract the lower bound, so minus cos of 1, and then okay, so what is cos of 1 and all of that? Of course that's going to be a constant, so this is going to be minus cos x3 plus cos 1. So you can actually bring the cos 1 in front, but that's not our interest. The issue is that this is going to be the integral after you have integrated with respect to t and then substituted the bounds. Now, but from what we have here, we are given that we should call s cube u. All right, so if I now substitute my s cube as u here, so that's now going to give me minus cos u then plus cos 1, so which has become a function of u, no longer a function of x. And that's why they said here that now that this one now is a function of x. So at first it's a function of x, but by the time you now substitute, so you will now, okay, in fact they actually removed this and they used x here, sorry, they used u here, and then in place of course you have your dt here, so of course this one will be a function of u. Okay, so that's exactly what is required. Then let me remove this. This is just to show us how we got that is a function of u. Okay, so while we continue with, okay, the solving, and then as we solve we feel what is necessary. So it now says finally if we now simplify, so what are you going to get? That's what we are now being asked. Okay, and so see what we have there. So you will now have that d dx of the integral of x cubed from 1 to s cubed of sine t with respect to t is going to be equal to, now if we now replace our s cube with u, so we'll now have the sine of t with respect to t. Okay, remember to put our brackets here. So this is now going to give us, recall that we also did something here, so we are going to have some substitutions now. And what is it that we did here? We actually got the value of du dx, so that means we are going to replace u now, dx with du. And what is it going to be? From here you would see that our dx is actually equal to du all over 3x squared. Okay, so but let's just leave it that way, and then look at what we have here. You are aware that if I have d of the x of my integral from 1 to u of sine t dt, okay, that I can actually, now remember, close your brackets, so I can actually do something here. I can choose to replace this dx with du, and then everything here will be multiplied by du dx, and I have not changed anything. You know why? Because this du can still cancel out this du, and my dx will come here, so which is still exactly what I have here previously. Okay, so the question now is, why did they introduce that? So that, let's see what that is going to be. The implication is that you can see that this is already in u, so whatever will differentiate it will also be with respect to u, because from the previous line we said that this function is going to be a function of u, and that's what we have here. So if this will be a function of u, then the derivative should be with respect to u, and that's why we are introducing this. But to now give it a balance, we'll now have what we have here. Okay, so let's now try to simplify that, and that's actually what we are now asked to do. All of this we're actually given, so let's now finish this simplification. So we'll have d of the u of the integral of this, like I said earlier, is going to be this one will be integral of sine is minus cosine of t, all right, and then remember you're moving from 1 to u, and then multiplied by the derivative of that. So remember, we got the derivative of that as 3x squared. Okay, that's du dx is 3x squared. So you are going to have this to multiply your 3x squared. Okay, so keep that one side, and then here we are now going to have so when we now substitute, this is going, or let me write that here. So if we substitute, we are going to have d of dx or d dx of, now you are going to get here, if we substitute u, we'll have minus cos u, and if we substitute 1, we'll have, remember I said it will give us plus cos 1. Okay, but the cosine of 1 should be 0. Okay, help me confirm that. Or we can leave it that way. You can actually leave it as cos 1, but then it's a constant. It's not, it's approximately equal to 1. It's giving 0.999 and then all of that. So, but we can leave it as cos 1 there, no problem. And then is multiplying 3x squared. Okay, so finally you are now going to have the derivative of this. And to take the derivative of that, that's going to be, remember, like you would see that some of the things we are doing here were actually captured in the previous question. You remember that there was a place we were asked to get the derivative of minus cos. Let's go to the previous page. So look at it here. So you want to take, remember this was integral, so to get back this, you differentiate this, and when we differentiated this, we got sine. Okay, so let's come back here. So it was actually a pointer to the things we are going to be needing in the following question. So if we remember that derivative is a linear function or a linear operator, so we're going to differentiate all of this one after another. So if we differentiate cos minus cos, like I said, it's going to be sine u, and if we differentiate this is a constant. Cos 1 is a constant, so it's going to give us 0. Okay, and so you just have only sine u, then multiplying your 3x squared, and so you are now expected to bring back your u, because nobody gave you u. We are actually the ones that introduced that, and our u was actually x raised to the power of 3, and so you replace it with that and then multiply by your 3x squared. And so if you check what you have, you're actually expected only to fill in here. So this was given, so the proper solving will give you sine s cubed, and that is the solution to this problem. Okay, so we have done question 1 and question 2. So let's see number 3 before we can have a very little break. Okay, so problem 3, the reason I want us to look at it is that it looks a little bit easy. So it says give reason why the integral from minus 1 to 3 of 1 all over x squared with respect to x does not exist. Okay, why does this integral why does it not exist? Okay, so of course you there are many things to see here, so but the one that is profound for me is the fact that the function is not defined over the interval. Okay, it's not defined over all points of the interval. It's defined at some points, but it is not defined at some point. So you can say there is a vertical asymptote at a particular point of x. Okay, so you can see that it does not exist since the function approaches infinity or negative infinity as x approaches 0. So remember that the interval given to us is from -1 to 3, and between this interval 0 is included. So 0 is an element of that interval, and your denominator here cannot be 0. So the limit of this as x goes to 0 is not defined. So you can now say that the integral itself, because by the time you integrate, you would still have to define a sum from -1 to that 3, and so but of course that is not going to be well defined. And so because at point 0, because when it comes to definite integral, you can actually break it in points. So if I choose to break it this way, in intervals, if I choose to break it from -1 to 0 of 1 over x squared dx, and then plus from 0 to 3 now of 1 over x squared dx. So you discover that this does not exist and this does not exist, because at point x equal to 0, you are going to get an undefined expression. So we can say that the function f of x equal to 1 over x squared is not defined. Is not defined at all the points of the interval. All the points of the interval of integration. So of course our interval of integration is -1 to 3. So it's not defined at all the points. Particularly, you can put that, particularly x equal to 0. So it's not defined at that point. Okay, so at that point it will make the integral not to exist, right? So now there are other things you can look at. So but this is a beautiful reason for which that integral will not exist. Okay, so and like I said, we should just look at this particular one, and then we'll take a break and we will be back. So when we come back, we are going to continue with problem 4, which I want us to see now before we go. Okay, so let me be using P4. When I was writing questions, I was using Q, so let me just be using P now in terms of problem. All right, so here we are given the integral of 2x plus 1 all over all over, here we have 4x squared plus 9, and then into x squared plus 4. So all integrated with respect to x. Okay, so we are to do this integration. All right, so that will be in the next section. Okay, so think about it, and then when I come back we will go into it. All right, see you in that next section. Bye. Please do give a thumbs up to the video, and then you make comments, all right? Comments. What do you think about the class? And then let us know, and we'll see you in the next one. All right. Okay, so